beginning chapter 5 with trig identities. And let's see what we have for trig identities. There are a buttload of trig identities that we're going to learn. I do want you to memorize these. Of course, a lot of them, like these, we know. These are nothing new. Your sine equals 1 over cosecant, cotangent equals cosine over sine. These are identities that we have already been using. They're the basic reciprocal and quotient identities. So you need to remember those. In addition to those, we have some new identities, just some other properties of trig functions we are going to use, starting with these three that are called the Pythagorean identities. I'm going to spare you the proof, but they're called Pythagorean identities because you would use a Pythagorean theorem and the a squared plus b squared equals c squared mess in order to prove this. The main, I'll tell you, the king mama jama identity that you need to know is sine squared plus cosine squared equals 1. Of all the trig identities, I have found that this one shows up more than any other. So make sure you know this one. That doesn't mean ignore all the rest, but if your brain only has room to remember one trig identity, make it this one. Tangent squared plus 1 equals secant squared, and cotangent squared plus 1 equals cosecant squared. Those are derived from this equation. I want to show y'all one way real quick that you can get these other two. Let's say you only know the sine squared plus cosine squared equals 1. These other two have escaped your mind. They've flown off somewhere. So we're going to pretend that we don't know these. What I could do to figure out those other identities is I could take that equation, the sine squared plus cosine squared equals 1, this one right here, and I am going to go crazy here, and I'm going to divide everything in this equation by sine squared. I can do that. It's an equation. Just whatever you do to one side, you have to do to the other. So I'm going to divide everything by sine squared. And when I divide everything by sine squared divided by sine squared is 1. Then I have cosine squared over sine squared. Well, we know that cosine over sine is equal to cotangent. So if it's all squared, cosine squared over sine squared would equal cotangent squared. And then 1 over sine is cosecant, except the sine is squared. So that's going to be cosecant squared. And you'll see that what I just did by dividing everything by sine is I just created this identity right there. 1 plus cotangent squared equals cosecant squared. Same thing, it's flipped the 1 plus cotangent. We could generate this one, the tangent squared plus 1 identity, the exact same way. Except instead of dividing by sine squared, I could go crazy and divide everything by cosine squared. So divide by cosine squared. Whoa. Divide every single thing by cosine squared. And if I do that, sine over cosine is tangent, except it's all squared. Cosine over cosine is 1 equals 1 over cosine is secant, except the cosine was squared. And that gives us this identity. So if you only can remember sine squared plus cosine squared equals 1, you could generate the other two by dividing everything by either sine or cosine. So there's that. Some other identities, and this is a whole lot right here. You don't see these as often. These are not as common. These are called cofunction identities. The name co, like as in cosine and cotangent and cosecant, is because those are the cofunctions of sine, tangent, and secant. And what this identity is saying, to assign some real numbers to this, let's say I had the sine of 20 degrees. Following this property, sine of 20 degrees would be the same thing as the cosine of 90 minus 20, and 90 minus 20 is 70. Well, if you look at 20 and 70, those are complementary angles. If you remember back in geometry, two angles that add up to 90 degrees are complementary, and that's what the co stands for. The co in cosine, cotangent, and cosecant stands for complementary, which means if you're taking those, oh gosh, how do you spell complementary? Is this right? I don't know. So if you have sine and cosine of complementary angles, they are equal to each other. Same thing for cosecant and secant. If I did the cosecant of, say, 10 degrees, that would be the same thing as the secant, and the complement of 10 is 80. So secant of 80 and cosecant of 10 are the same. You could also put these in radian mode by, instead of saying 90 degrees, you could say pi over 2 minus theta, pi over 2 minus theta, and that would be the same identity only for radians instead of degrees. I decided to give you the identities in degrees first because we can wrap our head around 90 degrees a little bit better. The even-odd identities, that goes back to your even functions and odd functions where f of negative x equals f of x and all that mess. Sine of negative theta, if you have sine of a negative angle, you can pull the negative out, and I'm kind of saying that in a bad way. But essentially that says if you have like the sine of negative 20 degrees, that would be the same thing as the negative sine of 20 degrees. Cosine, you can kind of ignore the negative. If you have cosine of negative 20, that's going to be the same as cosine of positive 20. Notice that the cofunctions have the same properties as the main three. Sine and cosecant, not cofunctions, the reciprocals. Sine and cosecant are reciprocals, so they have the same property. Cosine and secant are reciprocals, so they have the same negative properties. Cosine and negative theta is cosine theta. Secant negative theta is secant theta. Same thing for tangent and cotangent. They are reciprocals of each other, and so they have the same negative property there. All right, so using these identities, I just spent 6 minutes just going over the identities. Using the identities, what we're going to do first is we're going to simplify some expressions. And I try not to sugarcoat things. This is something that I'll just be honest with you, you're probably not going to like this. And it's because there is no cut and dry rule. Y'all tend to like formula-driven math where you can just kind of open up your little recipe cookbook for math and follow the steps and get your answer. That doesn't work here. Basically, all we're going to do is we're going to play with these equations, and we're going to use all those identities, whatever we can, in order to make this a little bit cleaner. So I'm looking at cosecant times secant minus tangent. There's a lot going on there. 3 different trig functions. What I'm actually going to do first with this one is I'm going to turn them into sines and cosines. I know cosecant is the same thing as 1 over sine theta, or sine x. I know that secant is the same thing as 1 over cosine. And I know that tangent is the same thing as sine over cosine. So all I've done is I've used my identities to turn each one of these 3 functions into sines and cosines. If you're multiplying 2 things, that's the same as 1 over sine x cosine x minus sine x over cosine x. Let's see, and what can I do with that? We are subtracting 2 fractions now. So what I'm going to do, I'm going to get a common denominator, and that's a fairly common approach to problems like this. If nothing cancels, which I was actually hoping that something would cancel and multiply and go away, nothing canceled, so I'm going to get a common denominator and combine these. They both have a cosine, but this one here is missing a sine. So I'm going to multiply top and bottom of this second fraction by sine x, which would give me sine times sine would be sine squared x over cosine x times sine x. And this one over here I didn't change, 1 over sine x times cosine x. Now that I have a common denominator, I could combine that into simply 1 minus sine squared all over cosine x times sine x, or sine x times cosine x. It really doesn't matter. And now I've got to find a way to play with this. 1 minus sine squared kind of looks familiar. Do you remember that King Mama Jama trig identity I told you about? Sine squared plus cosine squared is equal to 1. If I went absolutely crazy and I subtracted sine squared from both sides of this equation, I would end up with cosine squared theta is equal to 1 minus sine squared theta. And what I've got right here is 1 minus sine squared x, or 1 minus sine squared x. That's the same identity I have up here, except it's x instead of theta. That means that that turns into simply cosine squared of x divided by sine x cosine x. Now I can cancel. I have a cosine on top. I have a sine times cosine on bottom. There is no addition or subtraction, so that means it's okay to cancel. I'll cancel this one cosine with one of these. That leaves me with cosine over sine. And cosine over sine, I know, is cotangent x, and that would be your answer. That's as simple as that problem will clean up. And that takes a long time, and there's a lot of just playing around and touchy-feely stuff, but that's how you work that problem out. You really just play with it, and you hope that eventually you stumble upon the right answer, and that happened. So there's that problem. Let's move on and try, this one. This looks scary, doesn't it? Let's see, 1 minus sine squared and cosecant squared minus 1. You know, that, actually 1 minus sine squared we just did, didn't we? Didn't we say, yeah, cosine squared equals 1 minus sine squared. So that's kind of playing around in the back of my mind. I know that cosine squared is equal to 1 minus sine squared. So I bet you the first thing I need to do is I'm going to take out 1 minus sine squared theta, and I'm going to plug in cosine squared theta in its place, or x, cosine squared x. Okay, that's over, and I'm looking at cosecant squared minus 1. Let's see, let's go back to our identities, because there was something with cosecant squared. Let me go back and see if I can find it. Let's see, cosecant squared. Here it is. Cotangent squared plus 1 is equal to cosecant squared. So let's use that. So I know that cotangent squared of an angle plus 1 is equal to cosecant squared. Whoa, what did I just do there? Cosecant squared. Let's see, but I need cosecant squared minus 1. Maybe if I just subtracted 1 from both sides, that would give me cotangent squared is equal to cosecant squared theta minus 1. That's what we have, cosecant squared minus 1. So I'm going to take out the cosecant squared, and in lieu of cosecant squared, we will put in cotangent squared because they are equal. So now I have cosine squared over cotangent squared. And I want to know if that cleans up anymore. Does that clean up anymore? I'm trying to separate these so they don't look like they're blended together. Anyway, all right, let's see. Hang on, I've got to sneeze. Hold on. What's going on here? Backfired. No sneeze. That's disappointing. All right, so I'm playing with cosine and cotangent. I don't know of any identities that tie those two together. I like cosine squared. I'm going to leave it as it is. And the reason I like cosine is because I generally prefer to have sines and cosines over anything else. My denominator, however, I'm going to change cotangent into cosine squared over sine squared. So cotangent is cosine over sine. Since cotangent was squared, we will simply square each of them. Then if you are dividing by a fraction, it's cosine squared over that fraction. If you divide by a fraction, you multiply by its reciprocal. So I'm going to multiply by sine squared over cosine squared. Hey, and look what happens. Look what happens. Cosine squareds cancel. Ka-chow. Ka-chow. That leaves me with simply sine squared x. It won't clean up anymore. That's as far as we're going to go with number 2. So that one took 3 minutes. We're getting better. We started with a 5-minute problem. Now we're down to 3 minutes. By the time we get to the end of this, maybe we'll be able to knock them out in 1 or 2 minutes. Let's see. Yeah! Holy cow, look at all this. By the way, I haven't worked these problems yet. I just kind of got these out of a book, and I haven't practiced or worked these out. So I'm really not sure what's going to go on with this. And that's actually how you work these out. I'm not expecting y'all to simply look at a problem and know exactly what to do. These problems, you really just kind of play with it. It's kind of like a puzzle. You kind of play around with it until something finally falls into place. So what I'm going to do here, let's see. I have secants and cosecants and tangents. I do see something really nice. I see the exact same thing right here, secant and cosecant, as I see in the denominator. And what I would like to do is cancel those. I would love to be able to say and knock those out. However, that is against the rules because of this subtraction sign. You cannot cancel two things if there's subtraction anywhere. You can only cancel if it's multiplication. So what I'm going to do to make those cancelable, hey, that's a cool word, is I'm going to treat this like an STD. Y'all remember STDs? We've had STDs before, hadn't we? A single term denominator. I'm going to group that denominator as one big term, and I'm going to split this fraction up. I'm going to split it into secant x cosecant x over secant x cosecant x. minus, and then I'm going to split the other part up. I'm going to put the tangent over secant x cosecant x. Yeah. And now I'm going to play with those individually. The one on the left is beautiful because this is all multiplication. It's secant times cosecant on top, secant times cosecant on bottom. Everything cancels, which means this fraction on the left just turns into a big, sexy 1. So we're going to leave that as 1. However, the one on the right is a little bit uglier. You know what we can do? I know in the back of my mind that secant x is 1 over cosine, right? Right? That also means that cosine x is 1 over secant. They are reciprocals of each other. Same thing with cosecant and sine. I know that cosecant x is 1 over sine x, and sine x is 1 over cosecant x. So what I can do is I could actually grab this secant x, and I'm going to pull it up to the numerator right here. I'm going to stick it up here with the tangent, but if I move my secant from bottom to top, I essentially am flipping it. So it's going to turn into cosine. That secant is going to become a cosine. So I pull the secant out of the denominator, stick it on top, it becomes cosine. My tangent, I'm leaving there. And then my cosecant, I'm going to do the same thing. I'm going to take this cosecant, which is in the denominator, and I'm going to move it to the top, which essentially flips it. It takes it from denominator to numerator. That gives me a sine x in the numerator. Good? So basically, I've gotten rid of that fraction. Now I'm going to play around with this some more. I have a cosine, a tangent, and a sine. I know that tangent can be rewritten as sine over cosine. And then the nice thing about that is I can now cancel. I have a cosine on top and bottom. Those cancel. And it leaves me with sine times sine. So that's 1 minus sine squared x. And 1 minus sine squared x, this is the third time we've seen this one. That is cosine squared x. So there's our answer. How long did that one take? About 4 minutes? Nah, geez. Now our time's getting all boogered up again. What do we think? Tricky, huh? It's just, the only way you get good at this is by doing several of them and you start learning what tricks to look for. Let's try this one. Let's see. I haven't tried this one yet either. We have two different fractions. We actually ran into that earlier. If we go back and look at number 1, I changed the way this was written and I had two different fractions. And my solution to this was to get a common denominator. I'm going to do the same thing with number 4, except my common denominator for number 4, let's see. I have secant plus 1 and I have secant minus 1. My common denominator, we're simply going to multiply those two. So I'm going to multiply this fraction over here by secant x plus 1 on top and bottom. This one over here, I'm going to multiply top and bottom by secant x minus 1. Yeah. Okay, so let's see. That gives me cosine times secant x minus 1. If I distribute that, cosine times secant, I'm simply going to write cosine x secant x minus cosine times 1. So I'm simply distributing cosine times both of those. Cosine times 1 is cosine x. And then plus, and then I'm going to distribute my cosine here. Cosine times secant, cosine x secant x. Cosine times 1 is cosine x. And then on bottom, I've got secant x minus 1 times secant x plus 1. When you add things, you don't add the denominators or anything. So that's going to leave me with secant x plus 1, secant x minus 1. Then we start seeing how this cleans up. Let's see, I have a minus cosine and a positive cosine. This negative cosine will cancel this positive cosine. And then these two things are exactly the same. So then I will combine these two into, see, that's 2 of them. So I have 2 cosine x secant x. On bottom, let's play around with that. Not a whole lot you can do, but I can multiply it out. And so that gives me secant times secant, which is secant squared. Secant times negative 1. 1 times secant. And 1 times negative 1. And I look down here, and I can cancel these also. Negative secant times positive secant. And let's see, I'm going to play around with this. We still need to do some playing. 2 cosine x times secant x over, you know what, cosine and secant, I know that secant x is the reciprocal of cosine, right? I'm going to use that property right here. I'm going to take out this secant x, and instead of writing secant x, I'm going to change it to 1 over cosine x. That's going to be very helpful because cosine times 1 over cosine, those cosines cancel. They're no longer there. On bottom, I'm left with just secant squared minus 1. So on top, the cosine and 1 over cosine canceled to leave me with just 2. And then secant squared minus 1, there's another identity that says tangent squared of an angle plus 1 is equal to secant squared. If I move that 1 over, you get tangent squared is equal to secant squared minus 1. So secant squared minus 1 is equal to tangent squared. Whew! And we're almost done. Actually, you know what? As far as I'm concerned, this is about as clean as it's going to get. There's one last thing you could do. There's 2 over tangent. Tangent and cotangent are reciprocal. So if I pull that tangent squared to the top, it could be written as 2 times cotangent squared instead of 2 over tangent squared. I would actually be okay with either one of those two. I'm not too convinced that the right side is any cleaner than the left one here. So I would go there. Geez, that's 22 minutes. There was one more problem I wanted to do, but we'll just stop here, and we'll cry about this in class tomorrow.